All right, so our second atomization technique that we'll look at for atomic spectroscopy is a graphite furnace. And again, not an artist, but we'll sketch this out the best that we can. And so with a graphite furnace, what we're looking at is a furnace. And I'll again just draw this as a kind of cylinder here. Okay. And inside this cylinder is going to be a curved platform that's kind of suspended here. Okay, so this has kind of a curve to it, and then we're going to end up putting a sample port right here. Okay, so here's our sample port. This is where we're going to put our sample in, and this curved platform is called a Lvov platform. Okay. And so when we put our sample in here, it's going to sit right on this platform here, right in that kind of dip in the platform. And so what happens here? We have this furnace. We're going to heat up the furnace. Okay, we're going to rapidly heat it. And as we rapidly heat the furnace, what's going to happen is we're going to take the sample, and if there's any solvent still on the sample, it's going to effectively dry the sample first. So we'll dry it. Then it's going to pyrolyze it, which is a kind of heated decomposition. Okay, so it's going to dry the sample and then pyrolyze it. Pyrolyze the sample. Okay, and then it's going to proceed to atomize the sample. Okay, all the while now we're in the gas phase. Okay, so as it's pyrolyzing and atomizing, we get gas phase products. We might say that we've vaporized it in between drying it and pyrolyzing it. Okay, these processes take extremely high temperatures. You're talking in the 3,000 plus Kelvin range to pyrolyze and atomize. So these are not low temperatures for our furnace. They're very much aligned with what we would see in our flames from a flame ionization. Now, how do we make measurements with this? In the flame, we might put a detector on one side of the flame and take a look at it. But with the graphite furnace, where are we going to actually be looking? Okay, so we might shine a light in, especially if we're doing something like fluorescence. We might have our excitation wavelength path coming in, passing through the furnace, and then out. So this is our light path. And in this in particular, what we have with our light path is a nice long path length. So much like we talked about path length with cuvettes in UV vis spectrophotometry, similarly here, when we want to do atomic emission or atomic fluorescence, having a longer path length is going to be really helpful because there's more room for it to interact with the sample. Additionally, unlike with a flame, this is an enclosed furnace. In a flame, as your atomized sample is in the flame, it can exit the flame, right? This is not, a flame is not enclosed. Whereas here, once you have your sample atomized in the gas phase, it's not going anywhere. It's sealed in there until you specifically run like a purge line through it. So we might have some kind of a purge gas feed to be able to clean between samples. But overall, what we have is a pretty enclosed sample space. Okay. Now, in comparison with a flame atomizer then, what this means is that our sample's not escaping. It also means that we're more efficient in getting our sample into an atomized state than we are with the flame atomization, and so we get something that is an instrument that is much more sensitive than with a flame atomizer, and one that needs significantly less sample. Now, one thing that is a disadvantage with a graphite furnace is that you might get poor precision with manual injection. So if you're having to put the sample in through the sample port manually, you're not likely to do it in a very reproducible way. This can be helped with automation, but that's going to drive the cost of your instrumentation up. Additionally, the precision of the graphite furnace, the enclosed case, the making sure it's got adequate transparency for the light path, that's all going to make this ultimately a more expensive form of atomization than with your flame atomizer. But again, there's a trade-off. You can use less sample, and you can have it be more sensitive to a small amount of sample. So again, lots of trade-offs, as always, with instrument design.